Hi, and welcome to part 2 of our stochastic simulation session. In this session, we'll learn about another way to simulate stochastic epidemics, event-driven simulations. So for a diagram of what this looks like as it plays out, I have drawn a small population of circular individuals. Orange individuals are susceptible, blue are infectious, and yellow are recovered. And let's say at time 0, we start with an infection event, and now we have one infectious individual. After some amount of time to tau 1, we might have another infectious individual, another amount of time tau 2. For the second event, we might have another infection again, and then have a recovery, and so on. So this is an example of the Gillespie algorithm, but how do we get these time between events? And the events for that matter. But to start with the time between events, these tau are exponential waiting times in this case, and they're drawn from an exponential waiting time distribution. So a waiting time distribution is the distribution of times until an event occurs. So here I have a few examples of waiting time distributions, and you can think about the probability that an event happens in less than 2 days as the area under the waiting time distribution curve, and that varies based on the rate of the exponential distribution generating that probability density function. So for example, gray, rate 0.5, you have a smaller area than a rate of 1.5 in black. So the probability that the days since infection until the next event, in this case recovery, is a lot higher for a rate of 1.5 than it is for 0.5. Okay, just to summarize for the Gillespie algorithm assumptions, so we have finite countable populations, which we are often thinking of populations as being finite, so that's not a terribly undesirable assumption. We are assuming well-mixed contacts like the differential equation models that we've been looking at, as well as exponential waiting times. And one property of exponential waiting times that I should mention is that the processes that use these waiting time distributions are memoryless, which means that what happens next only depends on the current state of the system. So for example, if I was infected 5 days ago and I have a friend that was infected 2 days ago, the probability of either of us recovering is the same because it only depends on the fact that we're currently infectious, not on the history of when we were originally infected. So some additional notes. Noise is introduced by the discrete nature of individuals. And this is the Gillespie algorithm produces an event-driven simulation, which is nicely intuitive in that we're thinking about specific events happening, but it can be computationally slow, particularly for large population sizes. So to continue, and this will lead into the exercise computer tutorial for this session. For the event-driven simulations, there are two main things that we need to know. We need to know what happened and when did that event happen. So for what happened, in this case, we have two types of events. We have infection events, where a susceptible individual becomes infectious, and we have another event where an infectious individual becomes recovered. And you can see, so susceptible individuals when they're infected, move to the infected or infectious class. Recovery events involve infectious individual moving to the recovered class. And then for when did it happen, this will depend on the rates of the events. And again, as we saw in part 1, you can define these rates similarly to their analogous differential equations, where you have the hazard of infection, beta I over n, times the number of susceptibles S. And then for recovery, you have gamma I. So taking what happened and when did it happen, how do we decide what those values are actually? And in particular for the tutorial, these will be defined or set up as the event time or event type, sorry, and the event time. So make sure you look for that in the tutorial. As far as event types go, in this relatively simple model, we just have 2 types of events, and they each have a rate. So beta Si over n, the rate of transmission, we'll call lambda 1. The rate of recovery, we'll call lambda 2. And the time to the next event, tau, is distributed exponentially with a rate parameter that's equal to the sum of the rates of each of those events. And then to find out what type of event happens, we use the probability that the next event is type I. So Pi is lambda I over the sum of all of the rates lambda I for all I. And in this case, there are only 2 rates, 1 and 2. So the probability of transmission is lambda 1 over lambda 1 plus lambda 2. The probability of recovery is lambda 2 over lambda 1 plus lambda 2. It makes sense. Those are the only 2 types of events. If you add them together, the probability that your next event is one of those 2 events is 1. And we can also think about how the difference between lambda and 1 and lambda 2, whether lambda 1 is greater than lambda 2, makes sense in terms of the probability of what happens next. So if lambda 1 is a lot larger than lambda 2, the probability that the next event is type 1 or a transmission event is higher than the probability that it's a recovery event, for example. So another example of our pseudocode, again, we start always with defining our initial conditions. We have the same condition for our while loop. In order to proceed, we want there to be infectious individuals remaining, and that the time is less than the maximum time we specified. And then while those conditions are met, we're going to calculate the rates, determine the time to the next event, determine the event type, update our state variables, and update the time. So a quick summary, there are many sources of stochasticity, especially small population size, imperfect observation of cases, and environmental variability. The Reed-Frost model is a discrete time model where each time step is based on the infectious period, and the simple Reed-Frost models can be extended to chain binomial models once we start introducing stochasticity and link these probabilistic events that have arbitrary time steps and infectious period durations that are not fixed. And then, as we just saw in part 2, event-driven simulations are such that each event is modeled separately, and these may be intuitive in terms of thinking of one thing happening at a time, but one of the downsides of event-driven simulations is that they can be computationally intensive, especially when you have large population sizes. So thank you very much for listening, and I look forward to sharing the tutorial for this session with you. Talk soon. Thanks.